node and the successor on the other node. This too is not a safety property because it's not always true. Similarly, the fact that nodes should always have successors is also not a safety property. Aha, we say, here is a safety property. The join timer should always be scheduled. Suppose that initially the join failed because the network dropped the message. And I didn't retry the join because the join timer has become unscheduled. So we write this as a safety property and we pass it to the model checker. And we run the system. And we wait. And wait. And wait. And wait. In this particular case, this is not related to the bug. The bug was not that the join timer became unscheduled. So we need to do something else to try to find the bug, and this finding it in this mechanism sort of suggests that we have to have some idea of what the bug is before we can use the model checker to discover an execution violating it. What we'd like to be able to do is to specify a liveness property. So a liveness property is essentially always eventually P, or basically eventually something should always happen. In the case of pastry, eventually the nodes should form a ring. In the case of a file distribution protocol, eventually all the nodes should receive the file. So, nodes forming a ring, that's a liveness property. Node pointers being symmetric, that's another liveness property. Nodes having successors, another liveness property. We want to be able to specify liveness properties. So why can't we do this using existing model checkers? Basically the problem is this. If you start at the blue state as the initial state, and you exhaustively explore the gray rings, if you exhaustively explore the state space around the initial state, you may discover some violations of known safety properties. But what can you say about all of the states that have not violated any safety properties? You're not likely to have any states that reach the liveness properties because these may take hundreds of steps in order to reach, where you will not probably be able to search more than 30 or 40 steps exhaustively. So what can you say about these properties? Are they bugs? Going in and looking at each one independently is going to be a huge overhead, and you're not going to want to, especially given that most executions from the periphery of the state space you explore will, in fact, eventually reach the liveness properties, the live states, if you let them run long enough. On the other hand, you may have an execution that runs on and on and on and on and on and never reaches a live state. So here we're going to hypothesize that there's some dead state region, some dead state space, that once you enter the dead state space, you cannot escape from it, right? Once you've been buried, you can't crawl out. You're dead. And we further recognize that just before entering the dead state space, the execution could have gone a different direction. And having gone a different direction, it could reach a live state. So how can we use this to augment model checking to find liveness violations? Well, what we do is we start with the initial state, we run a random execution. If the random execution reaches the live state, then we haven't encountered any bugs so far. We haven't encountered any dead states. So then we exhaustively explore up to some depth, and every state that we encounter, we run another random execution. We continue this process until eventually we've come across a state that when we run a random execution from that state, it does not reach the live state space, despite running for an order of magnitude more steps than any of the other executions. We suspect this might be a bug. And now we proceed to try to figure out where along this execution the bug is. Unfortunately, it's an 80,000 step execution and a 2 GB log file. Now, I spent a few hours trying to sift through one of these log files to try to figure out where the bug was, and I grew tired. You don't want to debug your system in this fashion. So we had to develop another technique to figure out whether or not there was a bug, and if there was a bug, where the dead state space was found. The solution, however, is quite simple. You take a prefix of the execution, and you branch it. You run another random execution from that state. If you reach the live state space, you know that you haven't entered the dead region yet. You now grow forward exponentially until you find a state that when you do branch, a step that when you do branch, no matter how many executions you run, 40, 80, 120, none of them reach the live state space. Now, this is not a guarantee. It's a heuristic. But it's an awful good one. We haven't had any failures in this case. So we'll hypothesize that this is a dead state space. And now we can use a binary search to isolate down to the one state where before that step we have proof, we have a path that reaches the good state space. And executing a single event into the future, just one event, one delivery of a message, one execution of a timer, or one application request, No matter what we do, having run hundreds of executions, none of them reach the live state space. At this point, the model checker says, I believe there's a bug, and I believe the bug is related to whatever happened in that step right there, the critical transition, the transition from not being dead to being dead, from just being sick to being dead. Okay? Now, I mentioned the fact that we haven't had any errors. What I mean is we haven't had any cases where there was a critical transition identified and there was not a bug. The critical transition has been off by a few steps, up to 4 steps in the experience that I've seen. But 4 steps, that's enough for a programmer to look at and say, well, it could have happened in this range. So that's our experience with the critical transition. So we take this technique and we apply it back to the pastry bug. Now remember, of course, that in addition to the ring that pastry is maintaining, there's the routing tables, and they'll actually be important in understanding the bug. We run the model checker on pastry, and after running for a while, it outputs this sequence of steps, which includes as step 5 the critical transition. We'll walk through these steps. First, node D, as part of the normal pastry protocol, sends a message to node F, which among other things alerts node F that there is a node called A. This is just normal, periodic, hello, how are you doing, what have you been up to lately protocol for pastry, maintenance. Next, node A departs. Nodes B and F detect that node A has departed and correct the ring in its absence. Node A comes back online, and then, in the critical transition, node F receives the message from node D telling it about node A. At this point, our implementation updated the routing table to point to node A. Now when node A tries to join, remember the goal is to route the message to A's closest peer in the ring. When F gets the message from D, it says, I know a node that's closer to A than myself. It's node A. So I'll forward the join message to node A. Node A receives its own join message and drops it because it can't join off of itself. Now, you might think that this is a simple bug to fix, and maybe it is. It's actually not. But your initial fix might be, well, don't forward a join message back to yourself, back to the node that's trying to join. In fact, we did that just to see what would happen. And what happens is that we find a case where 2 nodes fail, and they try to join, and their join messages are forwarded to each other. So it's not that simple. You have to do something a bit more complicated to recover from this bug. So George is happy. He's found his bug. He can fix his implementation, and he goes over to tell Fred about it. He says, Fred, I found your bug, okay? And Fred says, phew, I've been working on this for weeks, and I've added my debugging, I've run it on the internet, I've run it on my LAN, I cannot reproduce it. So he's happy to have found it, but it's way too much effort. But kidding aside, this message appears in the free pastry changelog for version 1.4.2. Basically what it says is, we found this bug in our system in the sense that we saw it exhibited. We tried for a while to fix it. We stopped being able to reproduce it, and so we gave up. This, I think, pretty much speaks for itself. Mace model checker, manual testing. I'm going with the model checker. So to recap, there's liveness and there's safety. In liveness, you specify the expected behavior, which you should know because it's the system that you're building. The system should do what you expect the system to do. And then it's fairly easy usually to say what the system should do, and you don't have to have any prior knowledge of the specific errors that can occur in your system. On the other hand, with safety properties, you're checking for specific errors. Now, it's a very good way to test for specific errors, but you have to know what the problems are in order to specify them. So the Mace model checker is going to find executions that violate liveness, and critically it will find the dead states and the critical transition leading to the dead state. We've applied the Mace model checker to many of our implementations. 4 of them are shown here. The first 3 had been well tested and run on the internet without knowing about any particular errors. Not that we hadn't experienced any errors, right? This is a distributed system. If you see a random error, the easiest thing to do is to look at it briefly. If you don't figure out what's going on wrong, you chalk it up to bad luck, some fluke that happened in the network, and you move on, right? So we've been running these systems for years, not knowing that they had these latent bugs. In the last case, in the cord implementation, we had done, this was an experiment. I tested it first by hand, and then I tested it using the model checker. I wanted to know, did the model checker find all of the bugs that I could find by hand? So, we found more than 50 bugs, and we found many more since that. In fact, most Mace developers use this as part of their daily testing routine. Whenever they want to test something, they use the model checker. Of the liveness and safety bugs, we found more liveness bugs than safety bugs, and actually that number is artificially inflated for safety because once you find a liveness